square root of 1 plus delta yi over delta xi quantity squared times delta x on the outside, because I just took the square root of it and it came back as itself. So if f is continuous from A to B, then by the mean value theorem, which you learned in Calc 1, there exists some value C that's between A and B such that f prime of C equals delta y over delta x. So when you guys were first learning how to do slopes of tangent lines, what you did was you took a secant line between 2 points and then you calculated delta y over delta x. And we saw, if you look back up here, that if you took this secant line and you slid it up so that it actually was just tangent to the curve, there was some value C in between those 2 points where that line was the derivative. And that's what this is saying. The derivative is equal to the slope. So if you remember back from pre-calc, right, when you first learned how to calculate the slope, you did it by change in y over change in x. So using this idea, we can now come back and replace delta y, delta x with f. So now we can say that S is approximately the sum from 1 to n of the square root of 1 plus f prime of some C between those two values, this guy is still squared, times delta xi. So just like we did with the rectangles when we were doing area, if we take the limit and we let delta x go to 0, so let's look back at our picture. If delta x drops to 0, that means the width of these triangles here are going to get smaller and smaller, and it's pushing the 2 points closer together. We're going to get infinitely many of these secant lines, and they're going to be so tiny that they're actually going to hug the line and they're going to return the true arc length. So if we take the limit as the absolute value of delta x goes to 0, right, of our sum, then what's going to happen is we're now going to get the integral from A to B of 1 plus f prime of x squared under the radical dx. So the delta x becomes dx. The limit of a summation, if you're creating infinitely many of these, it's going to turn into an integral. So that's where this integral comes from. If we go back to this first step back here where I factored out the delta x, you can see that I could have just made another switch and said, well, instead of factoring out delta x, I'm going to factor out delta y. And if I had pulled out delta y, I would have gotten delta x over delta y squared plus 1, and I would have pulled out the delta y, which would have become dy, and delta x over delta y would have been g prime of y. So if you go back and look here, you can see that these are actually equivalent. It was just one algebra change when we did the proof that would have made it different. So as long as it's algebraically possible, you can calculate arc length as a function of x, or you can change the variable y and set the integral up this way. Now, one thing to keep in mind here, notice I did a to b, c to d. The bounds on the integral have to match the bounds on the variable. So you would look at the x coordinates, right, to do this guy. You would look at the y coordinates to do this guy. So let's actually look at an example of calculating the arc length of a function. So we want to calculate the arc length of this function on the interval 1/2 to 2. So what I want to do here is I want to build this radical right here step by step. So first thing is I've got the original function. And I'm going to like rewrite it just ever so slightly so it's easier for me to integrate using the power rule. So I'm going to say, well, that's 1/6 times x cubed plus 1/2 times x to the negative 1. So I just wrote it like this, so when I take the derivative, the power rule is easier. F prime of x is going to be 3/6 x squared minus 1/2 x to the negative 2. Now I want to put it back with no negative exponents. So 3/6 is 1/2 x squared, and I'll get minus 1/2x squared. The next thing I want to do is I want to square my derivative. So when I square the derivative, I have to actually FOIL this out, okay? And I'm actually going to take this one step further since I have a 1/2 here. Let's just pull the 1/2 out front. So that way when I FOIL, I'm only FOILing this. Okay? So 1/2 squared is going to be 1/4. And then I'm going to get x to the 4th minus x squared over x squared, which is just negative 1. And then I'm going to get another one of those. So that's going to turn into minus 2. And then I'm going to get plus 1/x to the 4th. The next thing it says to do under the radicals, well, I have to add 1 to this. So 1 plus f prime over x squared is going to give me 1/4 times x to the 4th plus 2 plus 1/x to the 4th. So that came from, if we read this correctly, right, if I were to distribute the 1/4, I have x to the 4th over 4 minus 2/4, which is really negative 1/2, plus 1/x to 4x to the 4th. Well, if you add 1, the 1 wouldn't get added to either of these terms. The 1 would get added to the whole number. Well, if this is really negative 1/2, when you add 1, you now get positive 1/2. So if you check this, you can see when you distribute the 4 now, this is now a positive 1/2. But this thing actually factors. So this is the same thing as 1/4 times x squared plus 1/x squared quantity squared. So the reason that I wanted to factor it is because it's really hard to integrate stuff under a radical. You have to pretty much always use a u substitution. But I don't have any stuff outside the radical for my du. But if the stuff under the radical is something squared, then when you take the square root of something squared, it just comes back as itself. So let's set up the arc length integral and see what happens. So the arc length integral says use the bounds on x, and the bounds on x are 1/2 to 2 of 1/4 times x squared plus 1/x squared quantity squared, and all of that goes under a radical. Well, 1/4 is a square, and this is a square, so now all I have to integrate is 1/2 times the integral, oops, not negative, just 1/2 to 2 of x squared plus 1/x squared dx. So now I can integrate with a very simple power rule. So don't forget, this is the same thing as x to the negative 2. So when you add 1, you'll get x to the negative 1, and then you divide by negative 1. So that's why it becomes negative 1/x. And I'm going to integrate that from, or plug in 1/2 to 2. So when I plug in my bounds, I'm going to get 1/2 times, when I plug in 2, I'm going to get 8/3 minus 1/2 minus 1/2. When I plug in 1/2 here, I'm going to get 1/8 divided by 3, so that's 1/24. And when I plug in 1/2 in the denominator, the 2 is actually going to move up into the numerator. And this simplifies into 33/16. So these problems are algebra heavy. There's a lot of steps in building the integral, but if you take a really systematic approach and you're really careful, but make sure that you practice these quite a bit. So we're going to do a couple more of these just to make sure everybody's got the procedure down. So let's find the arc length of ln of cosine x from 0 to pi over 4. So the function f of x, right, is just the natural log of cosine x. The derivative of natural log, right, this is really natural log of u, right, so the derivative is u prime over u. So the derivative of the outside is 1 over cosine x times the derivative of the inside, which is negative sine x. Well, negative sine over cosine is just negative tangent. Then I need to square the derivative, so that just becomes tangent squared x. 1 plus f prime of x squared is just 1 plus tangent squared x. So when we set up our identity, we're going to get the integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx. Well, I can't really integrate this using a u substitution because my u would have to be everything under the radical. My du would be 2 times tangent x times tangent x, or times secant squared x, and I don't have any of that stuff outside. However, this is a Pythagorean identity, and 1 plus tangent squared is simply secant squared. So the square root of secant squared is just secant. And back in Calc 1, when you learned your, or when you first started learning integrals, excuse me, you learned all of your trig integrals, and this is a known, has a known antiderivative, and the integral of secant is the natural log of secant x plus tangent x, and I have to plug in 0 to pi over 4. So when I plug in pi over 4, I'll get the natural log. Secant of pi over 4 is the square root of 2. Tangent of pi over 4 is 1. Then I have to plug in 0. The secant of 0 is going to be 1, and tangent of 0 is 0. So what I end up getting is the natural log of the square root of 2 plus 1 minus the natural log of 1, but the natural log of 1 is 0, so my final answer is just the natural log of the square root of 2 plus 1. All right, let's do another one. So this one says we'll find the arc length of y minus 1 cubed equals x squared on the interval from 0 to 8. So 0 to 8 are actually the x values, all right? But I have to decide whether I'm going to set this up in variable y or whether I'm going to set this up in variable x. So if I try to solve this for y, right, I'd have to take the cube root of both sides, then I would get plus 1, and it would actually be pretty gross to take the derivative. It's actually easier to just take the square root of both sides and work in variable y. So that means that x would equal plus or minus y minus 1 to the 3/2, because remember the square root is just to the 1/2. However, if you look at the bounds on x, well, these are from 0 to 8. These are positive x values. So that means x can't equal something that's negative, so we actually would keep the positive case. So that means f of y is just y minus 1 to the 3/2. But if I'm going to work in variable y, I need to find the bounds on y. So if we plug in 0 for x and solve, we're going to get that y equals 1. If we plug in 8 for x and solve for y, we're going to see that y is 5. So my bounds on my integral need to be from 1 to 5. Let's take the derivative of this. So that's going to give us 3/2 y minus 1 to the 1/2, and then the derivative of the inside function is just 1. So the chain rule doesn't really get too crazy here. Now we need to square this, so 3/2 squared is 9 over 4, And remember, this is just the same thing as writing a radical. When you square a radical, you just get back itself. So now I need to figure out what 1 plus f prime of y squared is. So what I'm going to do is I'm going to distribute my 9/4 across when I add this up. So I'm going to have 1 plus 9/4 y minus 9/4, and that simplifies into 9/4 y minus 5/4. So 1 minus 9/4 is negative 5/4. So now my integral, remember I have to do the bounds on y, so that's 1 to 5 of the square root of 9/4 y minus 5/4 dy. Since both of these terms have a 1/4 in them, I can actually factor the 1/4 out, and the square root of 1/4 is 1/2. So I can simplify this by simply saying this is 1/2 times the integral from 1 to 5 of the square root of 9y minus 5 dy. So this can be done using a u substitution. I don't have any clever squares. I can't make the radical go away. So if I want to u sub this, I'm going to let u be everything that's under the radical. That means my du is just 9 dy. Well, I don't really have a 9 dy in here, so I'm just going to solve this for dy. So that means when I translate this into variable u, I'm going to replace dy with du over 9. I'm also going to go ahead and change the bounds. So when y equals 1, if I plug 1 into this expression, I'll get 9 minus 5, which is 4. So u is 4. And when y equals 5, well, 9 times 5 is 45, minus 5 is 40. So my new integral is going to be from 4 to 40 of 1/2 u to the 1/2. And when I plug in du, I have to plug in du over 9, so I'm just going to move that 1/9 out front. So let's combine these constants. So really what I'm going to have is 1 over 18 from 4 to 40 of u to the 1/2 du. So now I can integrate using a power rule. So that will be 1/18 u to the 3/2, and when you divide by a fraction, right, we multiply times the reciprocal. And so I can clean this up a little bit more. The 2 will cancel and this will become a 9, and 9 times 3 is 27. So what I'm going to get is 1 over 27 times u to the 3/2, so that's 40 to the 3/2 minus 4 to the 3/2. And you can actually stop right there. So in order to actually complete an arc length integral, you have to be able to deal with the stuff under the radical. And there's really only two choices. You can do a u substitution like we did here, where you call u everything that's left under the radical, and then you just hope you have enough components for your du, or you want to look to see if you can factor something into a square so that way you can make the radical go away. Some arc length integrals that you actually set up, you'll see problems in a lot of books sometimes where they'll say like set up but don't evaluate, and that's because technically until you get to unit 2 you don't really have any other methods to know how to finish one of those integrals if these two ideas don't work. Alright, so let's look at the third type. We've looked at things in functions of x, we looked at things in functions of y, but how do you deal with something if it's parameterized? And so what we mean by that is x and y are separately defined in terms of a third variable. So this third variable is t. So that means we're going to have to integrate everything with respect to t. So the way we set this up is you're going to look at x, right? So x of t is 3 cosine t. But the derivative of x with respect to t, in this case, would be negative 3 sine t. And then we're going to square the derivative. So when we square it, we just get 9 sine squared t. Then we're going to do the same thing with y. We're going to look at the function of y, and then we're going to take its derivative. And this works out to be 3 cosine t, and then we're going to square it. So now I have 9 cosine squared t. So under the radical says we'll take dx dt and square it and add it to dy dt squared. So this is going to give us 9 sine squared t plus 9 cosine squared t. Well, if I factor out the 9, I get 9 times sine squared plus cosine squared. Well, sine squared plus cosine squared is 1, so this all just simplifies to 9. So when I set up my integral, the bounds on t were given in the problem, and they said to integrate from 0 to 2 pi, and it's going to be the square root of 9 dt. Well, the square root of 9 is just 3, so I can factor that out front. So now I'm just integrating 1 dt. So this works out to be 3t, right, from 0 to 2 pi, and so I simply get 6 pi minus 0, so you just get 6 pi. All right, so the last section we want to look at is area of surfaces of revolution. So we took areas, right, and revolved them around an axis, and it gave us a 3D volume. Then we looked at how to find the length of the line. Now what we're going to do is we're going to take a line and revolve it around an axis, and what it's going to do is it's sort of going to create this hollow shell, but the shapes can be, the profile of the shape will match the profile of the original line. So it shouldn't seem crazy when you look at this that you kind of see the line integral pop back up in here. But what's going to happen now is our cross sections are going to be circles, but really what we're kind of doing is we're kind of doing the shell method all over again. We're going to get these little rectangles, these little bands around, and when you pop the band open, it's actually going to form a rectangle. So if I take this little gold band right here and I unravel it to make it straight, well, the length of it is the circumference of the circle, and then the height is my delta, or excuse me, the width of this right here is simply the length of the line segment. So this is actually going to be, oops, put this in terms of x, right? So this is going to be our line integral that we did. If we want to do this as a function of y, well then r would be measured with y, and we would use the function of y, right? Because we already derived that these two things are interchangeable. So you can see here that this little length right here, if we look at it here, there's our delta L. So that's why the line integral comes back up. So this sort of looks like a combination of like the shell method and the line integral, but what you're actually doing is you're summing up all of these bands all the way around, and you can see this thing's hollow. So this almost kind of looks like a little bit like a Coke bottle or like the top of a vase. So that's what's going to happen. We're going to, and then you'll see the profile of the shape will match. So now what we want to do is we want to calculate the surface area because there's nothing really going on inside these guys. So let's look at how to do something like this, all right? So we want to take the graph of y equals x cubed from 0 to 1. So there's the graph right here of y equals x cubed from 0 to 1. And then we're going to spin that around the x-axis, and it's going to create this trumpet. And this thing's hollow on the inside. So we want to find the surface area of this, right? So the radius, if I look at it right here, the radius is actually measured from the axis of rotation up to the line. So the radius is just the function itself. So there's our x cubed. But now we got to build the radical just like we would have if we were doing the arc length. So f of x is x cubed, but f prime of x is 3x squared. When we square it, we get 9x to the fourth, and 1 plus f of f prime of x squared is 1 plus 9x to the fourth. So the surface area is now going to be 2 pi the bounds on x were 0 to 1, the radius was x cubed, and then we multiply it times the radical. So more often than not, what's going to happen when you integrate these integrals is we can actually do it with a u substitution. So if I make everything under the radical my u, well, we can see when we take the derivative of this, it's going to drop down by a power. So I'm going to need something x cubed. But look what I've got out front. I've got some x cubed. So these are going to be 9 times out of 10 u substitution integrals. So let's set up the u sub for this. So I'm going to let the stuff under the radical, which is 1 plus 9x to the 4th, be my u. My du is just going to be the derivative of this, which is 36x cubed. And I've got the x cubed, but I don't really have the 36, so I'm going to solve for x cubed. So that means I'm going to replace x cubed dx with du over 36. And I'm also going to go ahead and change the bounds, because I don't want to have to deal with x anymore when I flip to u. So when x is 0, if we plug in 0 here, we see all we're left with is 1. And when x is 1, we'll get 9 times 1, which is 9, plus 1 is 10. So my new integral is going to be 2 pi over 36, because I'm just pulling this 36 out front, times the integral from 1 to 10 of u to the 1/2 du. So this is a really easy thing to integrate. 2 over 36 simplifies into pi over 18. This becomes u to the 3/2 times 2/3 from 1 to 10. And before I plug in the bounds, I can simplify the 2 and the 18. I'll get pi over 9, and 9 times 3 is 27. So I have pi over 27 times 10 to the 2/3 minus 1, or sorry, it's 10 to the 3/2, my bad, right? Minus 1 to the 3/2, which is just 1. So this is your final answer. You can stop right here. All right. So let's look at an example of one where we rotate around the y-axis. Okay. So when we rotate around the y-axis, we're going to have to work in variable y. And the r, right, that if we look at here, our radius, or sorry, we don't have to work in variable y, we can actually work in variable x. The r here, right, is x, right? So if you look from this out, we've got a length of x, right? And then the line itself is x squared. And we were given the bounds, the lines going from 0, 0 to square root of 2, 2, okay? So if we look at our function f of x, we get x squared. The derivative of this is 2x. Now, if some of you are wondering, could we do this in variable y? Absolutely we could. And I'm actually going to set up the integral to do this in variable y. We're actually going to do this one twice, right? So you'll see that x is just a little bit algebraically easier to work with. So the derivative of this is 2x. So then when we square that, we get 4x squared. And if we add that to 1, we get 1 plus 4x squared. So the surface area is 2 pi. The bounds on x are 0 to the square root of 2. Our r was just x. And our radical is 1 plus 4x squared dx. So once again, I can u sub this, right? If I have an x squared under the radical, I better have an x out front, and I do. So we're going to let u be 1 plus 4x squared. Our du will be 8x dx. I've got the x and the dx, but not the 8, so I'm going to solve this for x dx. I also want to change my bounds. So when x equals 0, when we plug in 0, we see that u equals 1. When x equals the square root of 2, well, the square root of 2 squared is just 2. 2 times 4 is 8. And 8 plus 1 is 9. So my new integral is going to be 2 pi over 8 times the integral from 1 to 9 of u to the 1/2 du. That's going to equal pi over 4 times u to the 3/2 times 2/3 from 1 to 9. And the 2 cancels with the 4 and gives me pi over 4, and 2 times 3 is 6, so I'm going to get pi over 6 times 9 to the 3/2 minus 1 to the 3/2, which is just 1. So I can, actually on this one I can keep going because the square root of 9 is 3. So the square root of 9 is 3, so that's the same thing as saying 3 cubed, which is 27 minus 1. And so I get 26 over 6, which is 13 pi over 3. Right? Let's see what would happen if we tried to work with variable y. So if we tried to work with variable y, then I would need to solve the equation y equals x squared for x. So x would be plus or minus the square root of y. I only want the plus case because I'm looking on the positive side of x. So that means our function of y is the square root of y. Then our r would actually be the function itself. Okay? So because when you're measuring out this way, you either get a distance x or you get a function of y. So if we take the derivative of this function, we're going to get 1 over 2 root y, and when I square it, I'll get 1 over 4y. So then 1 plus f prime of y squared is 1 plus 1 over 4y. So now, if I set up my surface area integral, I'll get 2 pi. Now I have to use the bounds on y. So if we look at the bounds on y, y starts at 0 and goes up to 2. So this would be 0 to 2 of the square root of y times 1 plus 1 over 4y dy. Well, since I have y to the 1/2 times something to the 1/2, I can actually move the y inside the radical and I can distribute it across. So this is the same thing as saying y plus, and if you multiply this by y, the y cancels and we get y plus 1/4 dy. Well, this is also can be completed using a u substitution. And if we want to u sub this, we'd say, well, let u equal y plus 1/4. du is just dy. And if I change the bounds, when y equals 0, u is 1/4. And when y equals 2, u is going to be 2 plus 1/4. So that's going to be 8 over 4 plus 1/4. So we get 9/4. So when I translate this into variable u, I get 2 pi times the integral from 1/4 to 9/4 of u to the 1/2 du. So this is going to be 2 pi times u to the 3/2 times 2/3 from 1/4 to 9/4. And this is going to give me 4 pi over 3 times 9/4 to the 3/2 minus 1/4 all raised to the 3/2. So this actually looks a lot grosser because you have to deal with fractions, but it's actually kind of doable because those are both squares. So we'll have 4 pi over 3. The square root of this, because remember you can do these in any order, you can do the square root first. This is 3/2. And if you cube 3/2, well, 3 cubed is 27, 2 cubed is 8. Well, the square root of 1/4 is 1/2, and 1 cubed is 1, and 2 cubed is still 8. So look what happens now. I get 4 pi over 3 times 26 over 8. I can actually cancel the 4 and get 4, right, over 2. and 26 divided by 2 is 13 pi over 3. So you would get the exact same answer if you did this in variable y or variable x, because it's just taking the line and rotating it around and giving you the surface integral. So if you're going around a horizontal axis, then the surface integral, right, is 2 pi from a to b of f of x, because the radius is the function, times 1 plus f prime of x squared dx. However, if you're going around a horizontal axis and you want to switch to variable y, well, that's 2 pi, and I'm going to use c to d to denote the bounds on y, and y equals f of x. So the f of x gets replaced with y, but the line integral, we already saw, these are equivalent, these radicals. So you can actually do it two different ways, in variable x or variable y. If you're going around a vertical axis, then the surface integral is 2 pi from c to d g of y times the line integral with respect to y, right? Or, oops, that should be dy. If we want to switch to variable x, well, in the same way the y values come out of f of x values come out of g of y. So we can say, well, this is 2 pi, going back to a to b because we want the bounds on x, of x 1 plus f of x squared dx. So one thing that's cool about surface of revolution is you can integrate on a horizontal or vertical axis with respect to either variable, as long as you understand that when you're measuring off a horizontal axis or the x-axis, the height of the radius is just the function itself. So if you switch to y, you have to know that the y values come out. So we're just literally translating y equals f of x. Same thing's true down here. When we read across a vertical axis, that's the function of y is the radius, but since the x values come out, we can say, well, x equals g of y. All right, that's it. I've loaded the problem set that goes with this on ELC. So just make sure that you complete these problems, and just see me in office hours if you have any questions.